Let's look at how to find a steady state vector for a 3 by 3 system. So in this problem here, look what's going on. So it says day by day, the day by day car rental agency has rents cars on a daily basis. Rented cars can be returned at the end of the day to any of the agency's 3 locations, A, B, or C. And here's how it goes. If a car starts in station A, then there's a 70% chance the next day it will return to station A, and a 20% chance it will move over to station B, and then here, right, a 10% chance it'll go to C. Right, so this is our transition diagram. From the transition diagram, let's create the matrix. So let's see, if we go from A to A, now A to A is 0.70, so we'll have 0.70 here, and then from A to B, that's going to be a 0.20. A to B is a 0.20. Put a 0.20 there. And then this better be a 0.10 down here, right? So if we go from A to C, because these have to add to 1, so let's just check it. A, there's the arrow. A to C, sure enough, is a 0.10, right? I'll go ahead and fill the rest of these in. So this is what I got for the transition matrix. See if you get the same thing. And I'm going to claim that because we have no zeros in here, only positive numbers, just to the first power, this matrix is regular. And since it's regular, that means it approaches some steady state. And that's what we want to do here, is find the steady state. So why don't we do this? Why don't we let capital X equal, okay, here's A, B, and C. Here's our steady state, right? We don't know what it's going to be for right now, so let's just assign those probabilities as variables. So in the long run, this, whatever number this is, this will be the probability that the car will be in station A. This will be the probability that this car is in station B, and the probability that the car is in station C. And this is the vector that we want to find. Now by vector, what I mean is a matrix with either one column or one row. We call that a vector. And this is the steady state, so we know that if we apply the transition matrix to the steady state, where should we be? Right back to the steady state, right? If you start at the steady state, make a transition, you're right back where you started, right? There's no change. So this is a matrix equation. Here's what it looks like for us. So here's what I've done. Here's T, right? There's T. Here's X. So T times X. Now I just left the second digits off because they're zeros. But I've got T times X equaling X. So let's just put that X in here. And let's multiply these matrices here together. Let's multiply those together. And you know how this goes, right? What do? We go over and down. So we'll get 0.7 times X plus 0.1 times Y plus 0.1 times Z. Okay, so here's our first row, over and down. Second row, over and down, so 0.2x plus 0.8y plus 0.3z, and the third row is the 0.1x plus 0.1y plus 0.6z, all right, and that's going to equal the other matrix, that matrix on the other side of the equal sign, x, y, z. Now, two matrices are equal, right? This matrix is equal to this matrix if and only if their components, corresponding components are equal. So this component here has to equal that component. So we get an equation. We get this equals this, and then this equals this equals this. I'll write those. So I just went ahead and wrote our system. So I got this equals this equals this equals this. There's our system. We need to solve this. Now, we know to solve a system of equations, you want all the variables on one side. So I'm going to subtract x, subtract y, subtract z. So let's start here by subtracting x. Now, be careful when you do this. Look what we've got. We've got 0.7x minus x, and then plus 0.1y plus 0.1z equals, and then on the right side, x minus x, that gives us a 0. Now, be careful here. This is 0.7 minus 1, right? Really, it's 0.7x minus 1x. So this is really, if you factor the x out, what have you got? 0.7 minus 1, which is negative 0.3x. Right, so I mean, we don't have to go through all that. You can see what's going to happen. 0.7x minus 1x. 0.7 minus 1, negative 0.3. So that'll give us this equation here. Negative 0.3x plus 0.1y plus 0.1z, that's equal to 0. Now in the second equation, let's eliminate the y. We'll subtract y. So if I subtract the y, do you see what's going to happen? We've got 0.8 minus 1. 0.8 minus 1, negative 0.2. Right? 0.8 minus 1, negative 0.2. So the second equation then is going to be 0.2x minus 0.2y plus 0.3z. That's equal to 0. And in that third equation, we're going to subtract the z. So I have 0.6z minus 1z, and 0.6 minus 1 is just like 6 minus 10, right? You get a negative 4, but this is decimals. So 0.6 minus 1 gives us negative 0.4. So we're going to have 0.1x plus 0.1y minus 0.4z equals 0. Now, this happened in the 2x2 example that we did in the last video. But look what happens here. See these first two equations? What do you get if you add these? I'm thinking you get the opposite of this equation right here, right? What do you get? You get negative 0.1, you get negative 0.1, and then you get 4z. So this equation here is just the opposite of the sum of these two. So this equation here is not really independent. This is not really a new equation. So this is a typical thing that's going to happen. When you have a 2x2, one of the equations will be dependent. If you have a 3x3, one of them will be dependent. If you have a 4x4, one's going to be dependent. So you can always just eliminate one of the equations, right? Just get one of the equations and replace it with another known independent equation. And that independent equation is always going to come from here. I'm going to write it up here. I'm going to go up here and see this, that x, y, z. You know that x plus y plus z equals 1, right, if you go down that column. So I'm going to replace this last equation with this one here. So here's our new system now. Our new system's right up here, so I kept the first two equations, but I replaced that last dependent equation with this one, x plus y plus z equals 1. Now all I have to do is solve this system, so I just have to remember what we did like near the beginning of the semester. I'm going to use a matrix to solve this. So what I'm going to do is I'm going to RREF, you remember that? Row reduced echelon form. I'm going to RREF, now I'm going to go down the columns, negative 0.3, 0.2, and 1, right, just the coefficients, 0.1, negative 0.2, 1, 0.1, 0.3, 1, and then 0, 0, 1. All right, so RREF that matrix, and we'll have our solution, our steady state vector. So here's what I got. Now you know how it starts is 1, 0, 0, 0, 1, 0, 0, 0, 1. We get that identity matrix, and I'll put the line in, and when I RREF this thing, I got 0.25, 0.55, and 0.20. Just check, do they add up to 1? 25, 80, they do. They add to 1. So our vector, our steady state vector is 0.25, 0.55, 0.20. And then what we can say is that in the long run, okay, in the long run or the long term, what can we say? 25% of the cars will be in station A, 55% will be in station B, and 20%, what is that? And 20% will be in station C.